Hello, this is lecture 19, sixth sem, Maths 3, Unit 1, Topology-1. Topology-1 by Ramanjan sir, Department of Mathematics, Tungal College, Jamkandi. So we have still a few theorems on the neighborhood and the limit points of a set. So already we completed theorem 1 in lecture 18, whereas now theorem 2 let x comma tau be a topological space. Be a topological space. Be a topological space. And a comma b are subset of x. Then the first one, if a is subset of b, then d of a is subset of d of b. So what is d of a? It is the set of all limit points. So second one, d of a union b is equal to d of a union d of b. So this is the theorem asked in the years successively 2015, 2016, 2017, next 2019, 2020. So successively they were asked in examination. Next. So take the proof for this. Proof. First one, let x comma tau be a topological space. Be a topological space. And a comma b be subset of x. A comma b be subset of x. X small one proof. Let x belongs to x belongs to d of a implies x is a limit point, because d of a is a set of all limit points. Suppose x belongs to a, x must be a limit point of a. This implies, this is the definition for the limit point, there exists an open set G containing x such that G minus set of x intersection A is not equal to phi. But G minus set of x intersection A is subset of G minus set of x, which is subset of B, since A is subset of B. actually is equal to A and also subset of B. This implies G minus set of X intersection B also not equal to 5. This implies X is a limit point of B. X is a limit point of B. This implies X belongs to D of B. Therefore, D of A, because X belongs to D of A in the beginning we are taken, whereas now again X belongs to D of B, so that D of A is subset of D of B. Next, we prove that the second one, D of A union B is equal to D of A union D of B. Next, second one, to prove, we prove that D of A union B is equal to D of A union D of B. Next, to prove this, D of A union D of B is subset of D of A union B, and D of A union B is subset of D of A union D of B. So A is subset of B and B is subset of A, then A must be is equal to B. Next, first we will prove this. First, D of A union D of B is subset of D of A union B. We have A is subset of A union B and B is subset of A union B. So take D on both sides. D of A is subset of D of A union B and D of B is subset of D of A union B. This implies D of A union D of B is subset of, both are the subsets of D of A union B. Take this as equation 1. Next, to prove D of A union B, next to prove D of A union B is subset of D of A union D of B. Let X belongs to D of A union B, and we prove that X belongs to the right side D of A union D of B. Then to prove X belongs to D of A union D of B. Suppose X does not belongs to D of A union D of B. D of A union D of B implies X does not belongs to D of A and X does not belongs to D of B. Let X does not belongs to D of A, what to be the next? Implies X is not a limit point of A. Implies there exists an open set G1 containing x such that G1 minus set of x intersection A is equal to 5. Next, x does not belongs to D of B, implies x is not a limit point of B. This implies there exists an open set G2 containing x such that G2 minus set of x intersection B is equal to 5. So take this as this is suppose intersection 5 is equal to 2 and this is to be now 3. Combining 2, 3, G1 intersection G2 minus set of x intersection A union B is equal to 5. This implies x is not a limit point of A union B. This implies x does not belongs to D of A union B. Therefore, D of A union B is subset of D of A union D of B. Take this as equation 4. From 1, 4, D of A union B is equal to D of A union D of B. The result proved. Next, some note I will take. Let x comma tau, note 1. Let x comma tau be a topological space. X comma tau be a topological space. And A is subset of x. Then A union D of A is called is closed. A union D of A is closed and A bar is equal to closure of A is equal to A union D of A. Next, second point. In real space R comma U, D of phi is equal to R and D of phi dash is also is equal to R in the real space, where Q is the set of rational numbers. Q is the set of rational numbers and Q dash is the set of irrational numbers. Next, so these are true in the real space. So let us see See that theorem 3. This was asked in 2016. Prove that real space prove that real space R comma U is separable Next, proof separable means that one of the set, either Q or Q dash, is countable subset of R. Let us see that proof. We know that Q is a countable subset of R. Q is the set of rational numbers. And we prove that Q is a dense set. Next, but Q bar is equal to Q union D of Q. Is equal to Q union R is equal to R, because Q union R is equal to R, because R is the bigger set, the set of rational numbers. Implies whenever Q bar is equal to R, Q is a dense set in R. Q bar means closure of Q. A bar means closure of A. Therefore, Q is countable and dense in R. Then R comma U is a separable space. So these are the two theorems you have to practice. It's very simple, that both theorems depending upon the neighborhoods and limits of the points. Thank you very much.